Okay, so in this section we are talking about L'Hopital's rule, which will be a rule that will help us evaluate limits using derivatives. And it will make a lot of limits that were really difficult a lot easier for us to compute. So first we need to talk about indeterminate forms. So when we're computing limits, and so I'll write this down so that we can remember. So when we're computing limits, we often end up with something where when we actually plug in the value that the limit is approaching, so I'll just say, plugging in, meaning plugging in the value that the variable is approaching, gives you something of the form zero over zero or infinity over infinity. And these are what are called indeterminate forms. So 0 over 0 is not well defined, and we could argue that it could have a lot of different values. And so we'll see an example of really why that's the case, why we call this an indeterminate form in a second. But just this does actually happen very often, especially when we're computing derivatives using the limit definition. We usually get something like this, where this would be of the form, so I won't write it's equal to, but I'm just being careful. So this is of the form 0 over 0, and then we often see limits like this where we have two polynomials and x is approaching infinity, and so this is of the form infinity over infinity, right? Okay. So these are both cases that we can apply L'Hopital's rule to. The other so there are other indeterminate forms. And so these are things like infinity minus infinity. This is not well defined. 0 times infinity, 0 to the 0. Of course, these two that we've talked about, 0 over 0 and infinity over infinity, and also 1 to the power infinity. So these are things that when we get them, when we plug in the value that our limit is approaching, if we get something of this form, any one of these, that means that we need to do some more manipulation or possibly apply L'Hopital's rule in order to deal with that limit. So we can't just leave this as our answer because it's an indeterminate form. And so the reason why we call these indeterminate forms is because we can produce any number of answers for this type of limit. So I'll show you an example where changing the function just a little bit will really change the limit of the function. So for this example, we'll need the fact that the limit as x approaches 0 of x to the n is equal to 0 for any, we'll say, positive integer n. So 1, 2, 3, and so on. And we can see that by just plugging in 0, and it gives us just plain 0, and there's no issues there. And then another fact that we'll need is that the limit as x goes to 0 of 1 over x squared, well, this is equal to infinity. And so if you graph this function, it looks like 1 over x, but on the left-hand side of the graph, this side also approaches infinity. So you get a vertical asymptote at 0, and since both sides approach infinity, the limit as x goes to 0 is equal to infinity. Okay? And so notice that if we take the limit, we want to compute the limit as x goes to 0 of x to the n times 1 over x squared for different n. Okay, and so notice that if you were to apply a limit law, you would get well, let's split it into two pieces. So this would be the limit law for products, and as we said, this first limit is 0, the second limit is infinity. So this is one of these indeterminate forms. It's this one up here, right? Okay, and now we'll see that if we evaluate these for different choices of n, we'll get different answers. So just in general, anytime you have any n, you'll get an indeterminate form of 0 times infinity, and then if you do more manipulation, you're able to get an actual answer, right? So if we take n equals 1, that would be x times 1 over x squared, which would mean, if we simplify this, that we get 1 over x, and this limit does not exist because as, so I'll draw a tiny little picture. 1 over x looks like this, right? So when we approach from the right, it is approaching infinity. When we approach from the left, it is approaching minus infinity, which means that the full limit approaching from both sides does not exist. And then if we plug in n equals 2, then we get x squared times 1 over x squared, and this simplifies to just 1, and the limit of a constant is just a constant. So you can see already we've plugged in two different values of n, we've gotten two different answers, does not exist, and 1. And now if we plug in n equals 3, we'll get even a different answer. Okay, so simplifying this, we'll get x, and the limit as x goes to 0 is 0. So that is 3 different answers for the same type of limit. All we've done is change the power of x in that first piece. Okay, so this is just to motivate that idea that if we have an indeterminate form of this type or any of the other types that we get, we don't know what the answer would be. So you might be tempted in this case to say that the answer is 0 because 0 times anything is equal to 0, but it turns out that infinity is so large and such a different concept than a number that we can't conclude that this 0 times infinity is equal to 0. So it actually is something you have to be careful with when you're working with infinity. Okay, so in the next video we will actually go over L'Hopital's rule and do some examples.